Hello guys, we are here to discuss what 3D memory technology is. So why 3D? With growing demand for high capacity storage and planar NAND nearing its scaling limits, the times are getting tougher to develop more capacity memories using planar NAND technology. The savior to this, the Samsung introduced in 2013 the industry's first 3D NAND device. Micron Intel in 2015 introduced a new architecture for memory that they call it as 3D X-point or 3D Crosspoint. So what is this 3D NAND and how does this save us? It is a memory architecture in which memory cells are stacked in vertical layers and horizontal plane instead of just using traditional 2D plane. This increases the capacity without having to reduce the size of a fabrication process. 3D NAND uses charge trap technology. This we will discuss in coming slides. Unlike DRAM, they are non-volatile. Unlike hard drives, there is no mechanical moving parts, which enables a smaller form factors to be created while the intrinsic speed of SSDs far outstrip that even the fastest mechanical spinners. So they are very fast. 3D NAND. How is it made? In 3D NAND, the polysilicon strips are stretched, folded over, and stood up vertically to form the layers of 32, 64, or even 128 pairs. The trick to building a 3D NAND is that you have to build each section of every floor perfectly aligned with each other. Each cell array is vertically stacked on top of one another to form a multi-billion cell chips. So this is a cell construction of a 2D planar NAND and a 3D NAND chip. So you can see at a 40 nanometer half pitch, the total area is consumed is 240 by 240 for building a 16-bit cell. On the other hand, a 16 cells of a 3D NAND chips are manufactured vertically. They would consume as much area as a single one of those 16 planar cell would be. So we are reducing the area by 1/16th of the ratio compared to what a planar NAND will offer us. And that's great. Now this is a cell structure of a 2D cell and a 3D cell. So 2D cell has a floating gate which is used for storing the electron charge. On the other hand, a 3D cell has a ONO, oxide nitride oxide, that uses a charge trap technology, and it is also called as a all-around gate because control gate surrounds the entire channel from all the sides. Now, what is the charge trap flash technology and its benefits over the floating gate? It uses a silicon nitride to store the electric charge rather than the polycrystalline silicon that we use in floating gate. This approach saves the manufacturing cost in the following ways. Fewer process steps are required to form the charge storage node, smaller process geometries that reduces the size and cost, multiple bits can be stored, improved reliability and higher yield. So 3D NAND architecture. There are many various architectures, but these are the three. That's BICS, bit cost scaling, TCAT, terabit cell array transistors, and vertical gate. So in BICS architecture, the oxide polysilicon are formed in the alternate layers over the silicon substrate. Then the holes are etched, the oxides are applied on the walls, the nitride that is used for using the charge trap layer, and then again the oxide is applied on the wall, and at the end there is a polysilicon fill. Now this is a TCAT architecture. Instead of polysilicon, we are replacing it with a nitride. So oxide and nitride alternate layers are formed on the silicon substrate. Then the holes are etched, and the poly is applied on the walls. Then the oxide is applied on the wall, and the nitride is removed to give a fin-like structure. So you can see it in the figure G. And then the nitride is applied, and instead of a normal metal, it uses a high-K dielectric, which improves the coupling between the control gate and the charge trap layer. And then there is a tantalum fill etched into it. So what are the benefits of TCAT over the BICS? So in TCAT, we use same structure but has a high K metal gate, so which improves the better coupling between the control and the charge trap layer. Then BICS transistors are made from the walls to the hole, walls of holes to the center. In TCAT design starts with the channel at the center and builds the transistor middle out. So TCAT process is also called as a gate last because the gate is formed in the end, and the BICS approach, it's called a gate first because the gates are formed first. So this is a vertical gate. It is an alternative to an BICS and TCAT, where channel current flows horizontally and the gates are stacked vertically. So there are various architectures of vertical gate, but we are seeing this architecture is called an island gate SSL decoding method. It embeds the SSL in each bit line. If you want to see the making of a 3D chip vertical gate, you can click on the link below. Now moving further, this is a 3D XPoint. This is completely new architecture that has been introduced by a collaboration of Micron and Intel. The 3D XPoint doesn't use electric charge at all. It doesn't have a transistor and a capacitor. So that's something amazing. So they are so denser. They can be, like, they say Intel has said that the properties of a 3D XPoint cell change when the cell is written and remain changed for a long time compared to what SSDs are capable of. I mean, that's why these are said to be a non-volatile memories also. They can be classified as that. It is 1,000 times faster than the SSDs. It is 10 times denser than the DRAM because it doesn't have the transistor and capacitor. Unlike NAND, 3D XPoint memory can also write data into smaller areas. NAND flash must be written in a relatively larger block, so smaller space is required. Now it is called as a crosspoint as those wires you can see this forms a X-type structure when you look it from the top. It is more denser than DRAM, more robust and faster than NAND flash. It is a grid of parallel and perpendicular wires basically, and that's how we call the single column is addressed. The column is the address space and it stores 1 or 0. So in old memory technology or NAND flash, the transistor detect the charge inside the capacitor to give 1 or 0. There are no capacitors and transistors here. So if you have two wires connecting each other, that is a unique cell. Now the SSDs, okay, they run at a speed of 550 to 600 Mbps, which is faster. The PCI Express top speed with the current technology is around 1000 to 1500 Mbps. But they say that Crosspoint is so faster that there is no bus in existence. So it will be interesting to see how various industries like look this technology as, because compared to what we have been using for generations, this technology has totally different architecture. For this, we have to think of how OS will use this. So we have to change the software as well as hardware, both. It is not like a normal SATA where we just plug in into a SATA location and we use it. No, it is not that way. It is totally a different architecture, and it will be very interesting how the industry reacts to this product. And now it will be like Micron and Intel has said that it will be available by the late 2016. So let's see how it will be taken by the industries. Thank you.